Okay, welcome to another Origin seminar this week. Today we have Dr. Bryce Bolin, who's visiting Tucson. He got his PhD in astrophysics in 2018 from the University of Côte d'Azur in France. After that, he went on to California and used the Palomar Observatory, working on solar system objects. After that, he went to the Goddard Space Flight Center as a NASA postdoctoral program fellow, where he is now. And today he's going to talk about planetesimals. Thank you.
Oh, thank you. Thank you for the introduction. So I'm going to, this is a talk in two parts. Let's see if I can, there we go. Part one is going to be on the size distribution of the original planetesimals. Part two will be on their volatile content. Well, as I said, it's a long talk, but I will go through this as smoothly as possible, and we can discuss at the end both parts. So very quick, very first, I know everyone here studies planetary formation, and you may be familiar with these already. But just to establish the parameters, we have the semi-major axis A that describes an orbit. Orbit is described as though it is an ellipse. And the semi-major axis is emanating from the foci. It is the mean distance at which an object is located around its orbit. The eccentricity is the deviation of this ellipse from a complete circle. And the inclination is the angle between it and the orbital plane. So first of all, we're talking about asteroids. Planetesimals are what we would say asteroids are the remnants of the original planetesimals. Here's one series, one of the largest that we've observed with a spacecraft. As you can see, it's very circular, very spherical at about 1,000 kilometers. Vesta, it's 530 kilometers, half that diameter. It's the next second largest asteroid after a series. And you can see it starts to become a little bit more oblong. It's not as perfectly spherical. And as we mentioned before, this is Dinkinesh, the asteroid that was encountered by the Lucy spacecraft on November 1st. It is a binary system. The primary is about 800 meters in diameter, and the secondary is about a quarter of that. But it's actually two objects. It has kind of a two-component shape, contact binary shape. This was viewed as a spacecraft was exiting the Dinkinesh system, and they could see the contact binary of the secondary at the sideways view angle. And yeah, as we were talking about before, you can't see the neck. But the point of showing all this is that for asteroids, the larger the asteroid, you have kind of more of a spherical shape. And as you get to smaller and smaller sizes, you get into more weird oblong shapes, especially for Dinkinesh and its contact binary. So these objects follow the size distribution that is somewhat consistent with this classic Dognani result, where you have this collisional cascade that produces an exponential size distribution, where you have many, many fewer smaller objects than you have larger objects. You have the biased main belt is more or less complete to about 1 kilometer, but we can somewhat understand the size distribution at smaller sizes based on the near-Earth asteroid population. So when we're looking at just the main belt, we're talking about asteroids that are between the orbit of Mars and Jupiter, located between 2 AU and about 3.5 AU. And there's a few things I want to note. I want you to see here is that these asteroids are plotted by their orbital elements and colored by their albedo. Albedo is the reflectivity of an asteroid. And as you can see here, clearly there's a trend going on here. The outer main belt, you have lower reflectivity. Inner main belt, you have higher reflectivity, but there is mixing. You see both a mixture of low reflectivity in the inner main belt and high reflectivity in the outer main belt. And another thing I want you to also notice here is that the main belt is crisscrossed by various resonances. The new 6 is this weird curvy line, and semi-major axis is a Sinai perimeter space. That is more prominent at lower inclinations in the inner main belt. And then you have these vertical lines that show the proximal locations of the mean motion resonances. There is some tapering as you go to smaller eccentricity, But in general, they're about here at 2.5 AU, 2.8 AU, and 3 AU for 3 to 1, 5 to 2, and 7 to 3 mean motion resonances. Another thing I want to discuss about the asteroids is that we talk about the reflectivity in the, say, mixing of high albedo and low albedo material throughout the main belt. But these actually correspond to distinct asteroid taxonomic signatures. So by looking at this as a distribution of mass, the inner main belt is much more massive and silicate-rich asteroids, which we call the S types and the V types, whereas the outer main belt is much more massive in carbonaceous asteroids, which we call the C and D types. What this mixture of material tells us is something about the dynamical history and evolution of the solar system. So we're talking about year zero, the accretion of the asteroids, the accretion of the planetesimals in the original planetesimal disk. That is step one. This occurred, say, within a few million years of the formation of the first solids in the solar system. How do the asteroids form? We have two scenarios, two mechanisms, let's say. First is that asteroids formed at all sizes, from very small kilometer scale to large sizes, where you have slow accretion of asteroids from small pebbles to medium-sized pebbles to boulders and so on and so forth to the largest 100-kilometer scale object sizes. This would produce a size distribution that is steep, where you have objects, you have a fewer number of large objects and you have a very large number of small objects. The other scenarios where you have asteroids form big, it's kind of like punctuated equilibrium, where you have a sudden jump from very, very small objects to very, very big objects. So you can kind of think as number one is forming from the ground up, and number two is forming from the top down. And the mechanism for this is we have a very famous person here who came up with this idea called the streaming instability, which basically allows you to aggregate mass into a small area without increasing its cross-section and causing radial drift. So you have this buildup of mass, such that the mass builds up to a certain extent and where it is gravitationally unstable, and can cause the collapse of material from aggregation of small dust-sized material into a large kilometer scale, hundreds of kilometer scale bodies. And there's some evidence of this around other protoplanetary disks that we see in the outside the solar system, which is a topic of high interest to me. If you know about it, I'd like to talk about it with you later. So the resulting distribution of this, say, top-down procedure is that you have many, many objects. You have many, many objects at large sizes, but very few objects at small sizes. So you form everything large, and then there's nothing small after that. So now we're going to talk about the mixing. So we mentioned that the main belt is mixed in taxonomic signatures, the inner main belt and then the outer main belt. So how did this happen? Well, so you have the formation of material. Let's say we propose a scenario where you have S-type material that forms inside the orbit of Jupiter, and C-type material that forms outside the orbit of Jupiter. There is some evidence of this, not cosmic chemics expert, but I know there is now cosmic chemical evidence for this occurring, where Jupiter forms and it blocks off pebbles that are drifting from the outer solar system into the inner solar system. So you have these two separate reservoirs that are separated by the orbit of Jupiter. But what causes the mixing is that you have the inward migration of Jupiter and Saturn. So this gray area right here is the current boundary of the main belt. And as you can see, where the C-type material was in red, the S-type material was in red, the C-type material in blue is being mixed, that came outside, that was formed outside, exterior to the S-type material, is being all mixed up and thrown inside the main belt. Curiously, you also get material from well beyond into the Kuiper belt that is occasionally thrown in, as you can see, is the pink particles. So you have mixing material not only from the C-type region, but also from the Kuiper belt region as well in the main belt. So one key thing here is that this inward migration of Jupiter step that causes the initial mixing causes a lot of depletion. Let's say a factor of several. But the largest amount of depletion comes from the second round depletion, which is due to the second late migration period of the gas giants. So you may have heard this before. It's called the NIRSpec model. There's some debate whether it occurred within the first 100 million years of the formation of solids, or if it occurred much later to correspond with something called late heavy bombardment. However, the latter scenario is not as favored nowadays, and the former scenario where it occurred earlier is. But regardless of when it occurred, the scenario is basically this: is that you had a massive planetesimal disk that formed between 16 and 30 AU, which exchanged. Sorry about this video occurring so quickly, but you exchange material with the Jupiter and this planetesimal belt, which causes Jupiter to migrate inwards, and the rest of the gas planets to migrate outwards. And when Jupiter and Saturn reach a 2-to-1 ratio in their orbital periods, this basically happens. Someone takes a brick and you throw it into the washer machine, and the solar system, the outer solar system, just goes kablooey. What that actually looks like in terms of plotting here is this is from the famous Nature 2005 paper of Saganis et al. You have the planets start to migrate. Jupiter migrates inwards and Saturn migrates outwards, and when they start to reach a 2-to-1 ratio, their orbits start to chaotically readjust themselves, which causes this destabilization of that planetesimal disk. However, not only does it affect the primordial Kuiper belt, it also affects the main belt as well. And so for the primordial Kuiper belt, we started out with 20 to 30 Earth masses, and now we only have 10% of an Earth mass in the current Kuiper belt. And in the main belt, we started out with about 1 Earth mass, and now we only have 10 to the minus 4 Earth masses. So this is the depletion steps of 2 and 3. And then we have the present day, what occurred whenever the late instability occurred 100 million years after the formation of solids to now 4.5 billion years later. And so what happens in that 4.5 billion years later, you have collisional evolution. You have the disruption of asteroid parent bodies, which creates many, many fragments. And this causes the initial size distribution to evolve. So you have the initial size distribution here. Let's say we start with the asteroids are born big scenario, where you have many large objects but no smaller objects, but the collisional cascade causes the size distribution to evolve relatively quickly. Over the course of 1 billion years, you have basically more or less the size distribution as it is observed today. So one of the other outcomes of these collisions is that you have the creation of collisional families. And the reason why this is important is because when you are talking about the formation of the original planetesimals, their subsequent collisional evolution, collisional families are a way to track that collisional evolution process that occurred over the last 4.5 billion years. So when fragments are created from the disruption of a asteroid parent body, they are dispersed in real space, but they remain closely linked in physical space. So this is the semi-major axis and eccentricity distribution of a very young asteroid family, less than 1 million years old, called the Charon family. And you have this correlation between semi-major axis and eccentricity that occurs if the disruption occurs near its periapse. If it's at apoapse, you have the opposite. You have an anti-correlation. And if it's somewhere in between, it more or less flattens out. But for the Charon family, it's occurred relatively close to when it was at periapse. And so you have this correlation between semi-major axis and eccentricity. However, what happens, as I'll talk about further later on, after a few million years, various effects start to disperse asteroid family fragments. However, for asteroids that are older than, let's say, 1 million years, we still do see signatures. We still see evidence of collisional families. That is, groups of asteroids that are linked as having a hypothetical common collisional origin. So this is on the left-hand panel here, this is the asteroids which have been dynamically linked as belonging to a common collisional group. And on the right-hand panel, you have the inclusion of color. So the left panel only uses the orbital elements, but the right panel actually uses color information from SDSS, additional information. And one thing that you can notice here is that for some of these asteroid families that are on the left-hand side, is that they're much more compact, where if you start to include the color information, they're much more puffed up. And what that means is that by using dynamics only alone, you're only getting a fraction of the asteroid family members. Additional information showing that there's these halos surrounding the clusters of asteroid families to not be included with the dynamics alone. And there's a reason for that. So this is kind of making a more emphasis on that. You have these kind of ghosts here. So this is an outline showing the location of where the core of several asteroid families have been removed. The Vesta family, the Flora family, and the Nisopelana family. If this removal were 100% perfect, that is, you had a perfect accounting of the inventory of the asteroids for each of these asteroid families, you would not see this pattern of this kind of ghost-looking guy. It would actually be homogeneous. You would see a homogeneous background with no patterns indicating the outlines of where these asteroid family fragments are clustered in orbital element space. So what is causing this, causing the dispersion of asteroid family fragments? One of these effects is called the Yarkovsky effect, where you actually have thermal recoil, which is inversely proportional to an asteroid size. That is, asteroids that are smaller move more quickly. And this is also tied to the physical attributes of the asteroid, such as their density. And so how this affects the dispersion of the asteroid family fragments is that the Yarkovsky effect causes prograde asteroids to drift outwards into the major axis, and retrograde asteroids to evolve inward into the major axis. And by evolving their semi-major axes, that's what these kind of yellow pathways are for individual asteroid test particles. They start to encounter the mean motion resonances that I pointed out before, like the 3 to 1, the 5 to 2, and the 7 to 8, and so on. And when the asteroids come into the regions of these resonances, their eccentricities start to increase stochastically. And by increasing their eccentricity stochastically, they can start to encounter planets, start to cross the orbit of the planets such as Mars, the Earth, Jupiter, and so on, which then causes their orbital elements to evolve drastically as they are gravitationally scattered. So what is the mean effect of this crossing of orbital resonances? Is that basically over time, asteroid family fragments start to diffuse. It starts to become a less concentrated cluster to a more diffuse cluster. So the left-hand panel here is showing the Eos family at its year 0. As soon as the asteroids are diffused purely by their ejection velocity caused by the destruction of their parent body, you still have this spreading in some major axis and eccentricity. However, the spreading pales in comparison to the spreading caused by these dynamical effects of the spreading of the asteroid's major axis and crossing into various resonances, which are shown here, and vertical line slices at 7 to 3 and 7 to 9, and the 9 to 4 mean motion resonances. In over 1.7 billion years of dynamical evolution, this basically erases the original signature of the asteroid family fragments. So another thing that can cause the fusion of asteroid family fragments is planetary migration. We mentioned earlier, you had the migration of the giant gas planets' orbits due to the exchange of angular momentum between the planetesimal disk and Jupiter. And this causes the asteroid families which were made before that planetary migration occurred to basically become completely diffuse in eccentricity and some major axis. But one thing I want you to notice here is that while the eccentricity and inclination spread out all over the place, the semi-major axis distributions remain more or less intact. So what you are preserving in this planetary migration scenario is the semi-major axis distribution that those asteroid family fragments had at the time that the planetary migration occurred. This is going to become very important in a few slides when I discuss really old asteroid families. So if you look at this in the semi-major axis versus 1 over diameter space, we mentioned before that the Yarkovsky drift is proportional to 1 over diameter. Smaller fragments drift faster than larger fragments. If you look at this in this parameter space of A versus 1 over D, over time, you see a V shape and a V shape that starts to spread. Retrograde drift inward, prograde asteroids drift outwards. And the V shape gets wider with time. And we know this is the case because with Gaia data, we can actually do shape modeling from highly precise Gaia photometry. We can do shape modeling of the individual members of asteroids in an asteroid family to determine their obliquity. And we find that indeed the inner V-shape halves for asteroid family V shapes are retrograde, and the outer V-shape halves for asteroid families are predominantly prograde. So this more or less confirms that we can use this as a reliable indicator to define the border and width of asteroid family V shapes. So I invented a technique where I sweep this V-shaped shape, let's say a kernel, over the main belt to identify asteroid V shapes. This is a test main belt background and with a synthetically injected asteroid family V shape of a few 100 billion years of dynamical evolution. And on the top panel here, you can see the metric quantified by sweeping this kernel and convolving it with the distribution of asteroids in A versus 1 over D space. And you get a maximum in the metric at the location where the V shape is. And you can do it also in the spreading direction, let's say in the parameter direction that describes the width of the V shape. And we find a maximum along in that axis as well as where the center of the V shape is located in some major axis space. So we apply this for the entire inner main belt. And we're able to identify the V-shaped halves of 3 distinct asteroid families. The first is the Eulalia family here. It's more easily seen in this metric space where we are sweeping the V-shaped kernel over the main belt. We see a maximum here that corresponds to the Eulalia family. We see a second maxima here in this phase space, which corresponds to the New Polana family. And then we see a third maximum, which corresponds to previously unknown asteroid family, which we call the primordial family. We don't have a name for it yet. But if you turn these V-shaped slopes, let's say distance from the center of the V-shape, you can compute the age of the asteroid family. So the distance is defined as the distance from the center of the V-shape to the edge, to the border of the V-shape for a set diameter, in this case, 0.5 kilometer. And then you divide that distance by the Yarkovsky drift rate for a 0.5 kilometer asteroid, and you get the age. Applying this technique to the primordial family, we get an age of about 4 billion years, plus or minus half a billion years. It's highly uncertain because the physical parameters which define the Yarkovsky drift rate are highly unconstrained unless we have precise shape and thermophysical modeling of the individual models, which we do not have yet. We only have this for a tiny fraction of all asteroids in the inner main belt. But taking into account the uncertainties, we have a central solution of 4 gigayears. However, another indication of the old age of this family is from the orbital distribution. We're able to identify a signature in some major axis space, this V shape. However, we see the elements of the other orbital elements for the eccentricity and the inclination are spread over the entire extent of the main belt. And the scenario in which this happens is where we have the spreading caused by the family fragments, some major inclination and eccentricity caused by the sweeping of resonances from the migration of Jupiter. So what this implies is that this asteroid family is at least as old as when the planetary migration occurred. And as I mentioned before, the favorite scenario for that is that it had to have occurred within the first 100 million years of the formation of the solar system. So it implies this asteroid family is older than when that occurred, and that it must be older than 4.5 billion years. So you're like, okay, well, that's great. You found some really super old asteroid family. What's the big deal? What does that tell us about the planetesimals? You told us you were going to talk about the size distribution of the planetesimals. And for like the last order of some factor of 10 minutes or so, you've been talking about just asteroids. Well, I'm going to get to that. So by using this method, we can actually parameterize where we think fragments of the asteroids which are fragments, that is, they are producing the collision of the disruption of some larger parent body. It's separated from those asteroids which accreted directly from the protoplanetary disk. And I'll show you what I mean by that. So the asteroid family boundaries, which we defined as the primordial family, Polana, Eulalia family, and the Flora family, are all contained within these colored triangles. However, within this golden triangle here, we see that there's something peculiar. If I zoom in a little bit and color and replot things, we see that this area right here, this triangular area here, is completely devoid of asteroids. This one right there is an outlier. It's a mistake. It has a taxonomy that is inconsistent with having a low albedo. This is just a plot of just only low albedo asteroids. So this is probably not supposed to be here. But what I want you to notice here is that these bodies down here, is that there are only large asteroids right here. And so what is that like? What I mentioned before is that you have a size distribution in the top-down planetesimal formation scenario where you have only large asteroids that are formed, but you don't have any small objects right there. So these asteroids right here, because they are not in this V shape, these are asteroids which have never experienced they're not a product of the disruption of a larger parent body. They accreted directly from the protoplanetary disk. They were not involved in the disruption of some larger parent body where they were produced as a fragment. So if we show all the asteroids, regardless of their albedo, high albedo and low albedo, we'll see that for the high albedo asteroids, this kind of void starts at around for asteroids larger than 35 kilometers. And for the low albedo asteroids, it starts for asteroids with diameter of 50 kilometers or larger. And if we model the effects of dynamical depletion and collisional evolution, we can set an upper limit on the initial size distribution of those planetesimals inside that void triangle. And we find that it has a 3 sigma upper limit of minus 0.71, which is much, much shallower than what you would get in the accretion model. So this is the size, these crosses are the size distribution you would get from the accretion model. And this is our size distribution here. And recent simulations by various groups, which include Herbert Clark and Schubert, show that the size distribution of planetesimals is consistent from streaming instability simulations over various areas in the main belt, whether it's from the inner main belt, the outer main belt, you get a size distribution which is shallow, like the one that we show based on the identification of the planetesimals from our asteroid family analysis. So this is a summary of part 1. If you have notes, if you have questions, take them down as a note, and we'll get to it at the end of part 2. So now I'm going to go to part 2. Part 2 is about the volatile contents of the original planetesimals. Part 1 was about the sizes, but now I'm going to talk about the volatile contents. So first of all, getting onto that, I'm going to talk about one of the coolest comets ever discovered. And I'm going to talk about why I think it's so cool. So this is a plot that shows the discovery date of comet and the heliocentric distance at which it was discovered. So I'm primarily an observer, so I kind of geek out over things like this. But you can kind of see here, there's like these inflection points in the discovery rate of various comets. So the first comet was discovered as Halley, was actually discovered way before the 1700s. So this probably would have to go all the way back. But various other comets were seen before Halley was officially discovered, such as Caesar's comet, which is around the death, like a year after the death of Caesar. But let's just say for the last, since the discovery of 1P, comet Halley, these are the statistics that relate to all comets that were discovered after that. So starting around 1920, you see an inflection point there, and then around just before the year 2000, you see another inflection point. So I think this has to correspond to, before 1920, this corresponds to some kind of advancements in astronomical techniques which enabled the discovery of additional comets. But around the year 2000, you had the proliferation of CCD devices. And so that really, and then also the opening of sky surveys like the Catalina Sky Survey. A lot of comets were discovered by Catalina Sky Survey. I would actually think that majority of the comets after the year 2000 have been discovered by Catalina Survey, but I don't have those official statistics off the top of my head. But I just want to show here is that we're reaching another epoch of, say, jump in the heliocentric distance discovery of comets very recently. So we had the discovery of C2017K2, which was discovered at 15 AU, and pre-recovery observations show it as being active beyond 15 AU, I think to 18 AU. And then we had this comet C2010U3 Bottini, which was discovered at 17 AU. But very recently, we had the discovery of this comet called C2014U-1, which was found in images as far back as where it was 30 AU from the sun in 2010. So I overlaid here approximately the sublimation lines for CO when CO2 starts to become active at around 13 AU, and where H2O starts to become active around 4.5 AU. And so this kind of gives you an idea of where comets are being found and what their principal activity drivers are at the time of where they're being found. But these distant comets are being found well beyond the distance of where CO2 and H2O start to become sublimated. So more about this UN-271 comet. It was officially announced a couple years ago, but it was actually detected in images as far back as 2010. It was found principally, it was officially discovered based on data that was taken by the Dark Energy Survey and analyzed by Pedro Bernardinelli and Bernstein, given the name Bernardinelli Bernstein. So when it was discovered, it had semimeter axis on the order of 10,000 AU, though getting the precise actual semimeter axis, it could be as high as 30,000 AU or 40,000 AU. It's basically near a parabolic orbit. But we do know that it has a very, very large semimeter axis on the order of thousands of AU, and it has a perihelion distance of 11 AU, which it will reach in January of 2031. So here's what it looks like. I took an image of it with Hubble Space Telescope in 2021. It clearly has a coma. It was not so clear that it had a coma based on ground-based imaging, given the poor resolution of ground-based imaging. But with high resolution of Hubble, see here, it's clearly a nucleus. It's got a fuzzy coma appearance. And images where we're looking sideways at the orbit, we can actually see there's a spreading, which indicates that it's of the tail, which indicates two things: that the particles in the tail are starting to be influenced, even at the distance at which these were taken, it's about 19 AU, by solar radiation pressure, and that the tail consists of material of different sizes, which is affected by the solar radiation pressure of the sun. Differently, smaller objects or smaller dust particles are pushed away from the sun more quickly than larger dust particles by the solar radiation pressure. And based on the fact that it has a semimeter axis of many 10,000 AU, we know that it comes from something called the Oort spike. This is a plot of the one over the semimeter axis of Oort called comets before they encounter the sun and after they encounter the sun, or after they pass their perihelion, let's say. So before they pass their perihelion, they have an orbit distribution that is highly confined within a very, very small 1/A range, which is around 10 to the -4, which we call the Oort spike. After encountering the sun, their 1/A's are spread out all over the place. Some go hyperbolic, some stay within positive 1/A, but they are spread well past this envelope of 1/A times 10 to the -4. UN-271 is right in the middle of that. It is an Oort spike comet, which means that it is encountering the planetary region of the solar system for the very first time. Another thing is, this thing is huge. So, as I mentioned before, it's observed by Hubble. We used to look at it in scattered light, but more importantly, a more important measurement was made by AMA, where it was observed in the submillimeter, where you actually see the thermal emission of the comet itself. And that is directly proportional to the diameter, which shows that it had a 140-kilometer diameter. This is the largest Oort cloud, dynamically new Oort cloud comet ever discovered. So what this gives us the unique opportunity is to study the volatile contents of a 140-kilometer comet before it has ever been heated by the sun since it was ejected into the Oort cloud. And so I'll talk a little bit more about that and what it implies. But as I mentioned before, you had this instability scenario where you had a depletion of material in the primordial trans-Neptunian disk between 16 and 30 AU. UN-271 likely formed inside that because the factor, most of the planetesimal mass was located there. There's only one Earth masses inside the orbit of Jupiter, but outside the orbit of Neptune, you had about 30 Earth masses. So it likely formed inside this region between 20 and 30 AU and was ejected, very likely ejected. But you had a factor of 400 depletion during the planetary instability. So this gives us an approximate guess of when it was ejected, when it formed and was ejected into the Oort cloud. And the lower limit on that is that it had to have been ejected after the sun cleared its birth cluster, because if the solar system was still in its birth cluster, you would have the complete depletion, you have the complete dispersion of the Oort cloud. You cannot have the creation of the Oort cloud after had to have occurred after the sun cleared its birth cluster. You cannot have the formation of the Oort cloud occur before the sun cleared its birth cluster. So how does UN-271 become an Oort cloud comet? Well, this is a very, very short time scale in which it is scattered by the orbit of Neptune, starts to have, let's say we assume a Q, a perihelion distance of 25 AU, and on a scale of a few 10,000 to 100,000 years, you are scattered to a semi-major axis of 10 to the 4 astronomical units. And at this distance, the dynamics of the galaxies start to become important. You actually start to become influenced by the tides of the galaxy. And so what this implies is that you have a circularization that occurs. So this is a plot that shows the time scale at which various effects occur as a function of their semi-major axis. And so the most important line I want you to see here is this TQ. T sub Q is the time scale at which the perihelion distance of a Oort cloud comet evolves outwards by 10 AU. And so for something that is has a semi-major axis on the order of 10 to the 4s, let's say 30,000 astronomical units, this time scale is a few million years. So it takes about 100 million years to go from a Q of 25 to a Q of 250. And we know that UN-271 had a Q of 250 based on the integration of its orbit. We can actually backtrace its orbit outwards, and we can actually see that it had a close encounter with a star about 2.5 million years ago, before which it had a Q of 250 AU. So this gives us about an approximate time scale of some tens to 100 million years for it to go from having a Q of 25 to 250 AU. Now, this 250 AU is very important, because this is the distance at which all the cometary volatiles are not sublimative. So H2O really only starts to sublimate inside 5 AU, and CO2 is about 25, CO2 is about 15 and 20 AU. But CO2 is the most hypervolatile of all the cometary volatiles, and it is active out to hundreds of AU. But the previous perihelion distance of UN-271 puts it completely out of that. So when it formed inside the protoplanetary disk, let's say within the first 10 million years of the solar system formation, and then when it was ejected into the Oort cloud, it had never been heated by the sun's heat to have started the depletion of its carbon monoxide. So what this gives us is basically the ability to measure its original volatile contents when it formed inside the protoplanetary disk. So another thing you're also asking, a good question here, is what about the collisional evolution? Well, for an object the size of UN-271, it does experience impacts, but it does not experience catastrophically disruption impacts. So this is a new simulation. So I showed you the collisional evolution of the main belt, but this is the collisional evolution of the primordial Kuiper belt. And what this shows us is that objects that are larger than about 80 kilometers, the large proportion of them, more than 98% of them, do not catastrophically disrupt. So UN-271 is an intact planetesimal at 140 kilometers size. This is a kind of a rogues gallery, again, showing all the largest comets. The next largest comet that came from the Oort cloud was Hale-Bopp. C202, that's a long period comet, likely originated from the Kuiper belt, but Hale-Bopp very likely came from the Oort cloud. But even Hale-Bopp at about 70 kilometers, it maybe only has about a 80% chance of not having been disrupted in a catastrophic collision. But UN-271 is more than 3 sigma. It very most likely never experienced a catastrophic disruption. So it is an intact planetesimal. So when the Director's Discretionary Program became available for JWST in cycle 1, I submitted an application for telescope time within a week. And I was the first approved Director Discretionary Program out of all of astrophysics for JWST. And the program was to use NIRSpec to measure the volatile contents of this comet. We know that it was active, something has to be driving this activity, but we do not know exactly what is driving the activity. But NIRSpec observations can allow us to make a direct measurement of that. Unfortunately, only one of the exposures worked when the observations occurred in December of 2022. There was a guide star failure, but we got a repeat of it in June of 2023, so it's fine. Here are what the IFU images look like. It's clearly an extended comet. It looks like a comet. We show the continuum. You can see the dust structure even within the smaller field of view of the IFU. You can actually see an antisolar tail. And then we see evidence of ice absorption, and we actually can see the CO2 and the CO. The distribution of CO2 is much more diffuse, much more extended compared to the distribution of CO. But here's probably what you all want to see is the spectrum, what does the spectrum look like? So we have here between a spectrum between 0.6 and 5 microns. We have ice absorption features at 1.5 and 2 and 3 microns. We see a Fresnel peak here, which is very important because that Fresnel peak shows us that this ice is crystalline. One of the theories of how comets could have activity at such far distances from the sun, even beyond the normal ice sublimation lines for cometary volatiles, is that you have the conversion of amorphous ice to crystalline ice, and that releases entrenched cometary volatiles. But in this case, we can see here the ice is crystalline. So the volatile activity that we see is being driven by ice that is sublimating in a crystalline state. And the volatiles that we see here are CO2 gas, and we see CO gas. So this is CO2 and CO gas that is sublimating as ice somewhere near the surface of this comet. And the proportion of these gases by their production is 10 to 1. So if you wanted to say we have to undo the thermal evolution that could have occurred while the comet was forming due to the location of radioactive nuclides, since it is a 140 kilometer size comet, it could have accreted enough radioactive nuclides to cause the differentiation inside its structure. However, if it formed late, when most of those radioactive nuclides could have occurred, which is conceivable, because the streaming instability is enhanced by a lower gas to dust ratio. If you have the depletion of gas in the protoplanetary disk at a later stage before its gas phase ended, you have a higher likelihood of streaming instability forming gravitationally collapsed clumps. So you could not have as much, let's say, thermal evolution from the radioactive heating from the comet. And so it's very likely that this 10 to 1 CO2 ratio does represent the original proportion, the original proportion of these contents in the protoplanetary disk where UN-271 formed. So this is a summary of part 2. So basically, the key takeaway with UN-271 is that it shows that comets could have formed large. And the fact that they form large does not prevent fragments which could have formed from the disruption of parent bodies like UN-271 in the primordial Trans-Neptunian disk from having volatile contents themselves, because even though comets form large, their radioactive contents after forming large did not completely deplete them of volatile contents, which we see here, direct evidence of, and JWST NIRSpec observations.
Are there any questions or questions online?
Questions online? Andrew.
Yeah, hey Bryce, thanks for.
Go ahead, Andrew. Yeah.
Can you hear me? Hello?
I think you're muted. Are you muted, Andrew?
I'm unmuted.
Somehow I cannot hear you. Can you?
Huh. Okay, I'll type it. Sorry.
Andrew, we cannot hear you.
I can turn on my
Yeah.
Yeah. Okay, I'll type.
If you want to type in the chat, I can see the chat.
Okay, they say remote participants can hear. I guess maybe it's the speaker in that thing, maybe,
Oh.
or something, or maybe the volume's turned down.
Do I need to?
Oh, gee. Yeah, but this remote control doesn't do anything with the volume.
Should we check if just on the machine itself if volume has been turned down?
Yeah, let's see. Like I can mute this one and then see whether that works. if you can hear.
Doing you.
Maybe you could try unmute and then speak whether we could hear you. Okay. I think.
So I have his question. So he says he is wondering about the albedo stripes in the intro figure. And are those indicative of families? So I think that this is what is meant by the albedo stripes. So yes, the asteroid family fragments have similar albedos. So not only do they group in orbital element space, but they also group in albedo space. So what you are seeing here, you're seeing these thin strips of albedo, let's say, or asteroids with similar albedo, is that the asteroid family is spreading in semi-major axis, but they are closely grouped together. They'll asteroid families that are formed as a fragment of a parent body will all have the same albedo. So within that dynamic, within that cluster and orbital parameter space, you will see asteroid family individual data points with the same albedo measurement.
Let me see if I can do this one. Oops. Yeah, I changed it, it will seem to don't work. I'm sorry about the problem with the speaker. So, Caitlin?
Okay, so two questions, and I guess I'll go in order. So first, when you were talking about this V shape driven by the Yarkovsky effect, it seems like that's dependent on the idea that half of things end up prograde and half of things end up retrograde for it to be symmetric. Is that right?
Roughly speaking, you can have asymmetrical obliquity distribution after an asteroid family has been disrupted. You can have, and there is evidence seen for that in young asteroid families, that is asteroids that are not so young that Yarkovsky hasn't affected their family fragments enough, but are actually young enough that even still they preserve some of the initial distribution. But over time, this distribution gets erased, and the obliquities of asteroids reorient themselves, and on average over secular time periods, half will have prograde, half will have retrograde.
Okay, so you do expect that symmetry for things that are sufficiently old.
Yes.
Okay. And then my second question is, I think I missed part of the story of getting these primordial abundances from this giant comet. Because, so am I correct that your idea that it starts out with a perihelion of 25 AU, it gets pumped up to 250 and then scattered back in? Is that right?
That's correct.
So the fact that it spent a lot of time at 250 AU, I understand why that would have reduced the loss of volatiles, but it had all the time in between 25 and 250 to lose volatiles the first time, right?
That's right. So it was scattered by encounter with Neptune,
Right.
to have a semi-major axis of tens of thousands of AU. And so in that time, yes, you can have thermal evolution, but we're modeling that. And based on the observed onset of activity of the comet, we know that it had to have spent less than 100 billion years in this state with a Q of 25. So we can actually put timing on when that occurred. The result from Duncan, Tremaine, and Quinn is sort of a average case approximation, but you can have a spread in the actual evolution can actually have it occur longer than that, and you can actually occur much shorter than that.
Right, so then I guess I don't understand how you can, right, either you know the primordial distribution and you can model the age,
Right.
or you know the age and you're measuring the primordial distributions, but not both.
I think we can get both. If we have a second volatile content that we observe as occurring at a different onset of activity. So we can say, okay, we can have one chemical species that evolves and starts to sublimate sooner, and that this had to have occurred at a further distance than a more volatile species. So if you have CO2, which starts to sublimate at 20 AU or say 25 AU, we know that it had to have been depleted more quickly from the outward end. And based on when it was seen to its onset, the time of its onset when the comet came back in, we can say, okay, that the heat depth had to have only gotten so far as to start to turn on CO2. CO becomes active anywhere out to 250 AU, so we have a very, very wide envelope for that. For CO2, you're between, let's say, 20 AU and 25 AU is when you would start to expect the onset of activity. So as soon as the comet starts to get out of that, CO2 starts to turn off. And by measuring the onset of activity when CO2 starts to become active as the comet's coming in, which we have, it had to have started when it was around 23 AU, because we see an evolution in the comet's volatile activity. We see that it's more or less quiescent beyond 25 AU, and then you have this huge jump in activity around 23 AU. So that tells us that CO2 started to become active sometime around 23 AU. And that actually gives us the distance at which heat could have permeated through the structure of the comet in the time after it formed, regardless of the time. Now, once we know that time, then we can start to say, okay, how much does the CO2 have to have been depleted at all in between that time when it was formed and when it was actually ejected? And based on that, we can undo what the depletion for CO2 was. But in any case, the limit that we see for ratio, the value that we're measuring for CO and CO2 is 10:1, which is higher than any other comet we've seen before at this distance. And it can only be higher, because if you took your comet and you ejected yourself earlier, you're preserving more of that CO2, and that ratio is only going to get pumped up. The CO2 probably was never depleted at all until just now when the comet encounters it. So that 10:1 ratio is sort of a lower limit. It could have been higher. How high is still something that we're.
I have a similar but more basic question. Do we have an idea what is the orbital period of this object? Has it ever come back? Because like tens of thousands of AU, so I guess it's never come back.
So tens of thousands of AU is a few million years.
So it also has time to come back to this like 11 AU as the perihelion point. So it encountered with the solar radiation.
So the 11 AU is recent. In the previous, so that is just its most recent, let's say, approach to perihelion. However, between that and the last time it was at 250 AU, it encountered a star, and in the last few million years. So while it was coming in, it encountered a star, which then it will cause it to evolve its orbit to have a decrease in its Q to 11 AU. But before encountering that star, its Q was at 250 AU.
So Andrew's question, if time from the collisional families, can the time evolution of collisions be constrained? For example, more collisions early on, or is completeness a problem here? In chat.
So I would say, yes, it is more difficult to detect old families than large families. So there is a backup slide that I have, but it basically shows that if you have, you basically more or less assume that the collisional evolution of the main belt has remained constant for the last 4.5 billion years. So the proportion of young families to old families should be more or less the same. However, you clearly see a decrease in the number of known asteroid families older than 2 billion years. So what that suggests, that it is a completeness effect, that is asteroid families which are more diffuse due to Yarkovsky spreading of their B shapes and the dynamical diffusion from very circular resonance are making them more difficult to detect, more difficult to distinguish from the background.
Okay, any other question here? I have a question about in your NIRSpec data, could you actually resolve the CO line, the lines and actually, if you were able to see the spectra? Yeah, I could see that obviously, yeah. So I wonder if there is the absorption means anything or.
So this bifurcation here has to do with the temperature, the rotational temperature of the carbon monoxide.
Oh, okay, so it's not any.
It's not isotope log.
Okay.
I wish it was, but
So that I was wondering whether. All right, so any other question? Any question here online? Okay, so otherwise we'll say thanks to Bryce. And